Legend says a young Galileo sat bored in a cathedral, watching a lamp swing overhead. And he noticed something strange. Big swings, small swings, they all seem to take the same time. That idea that a pendulum keeps perfect time no matter how far it swings is almost true. Almost. And today we're going to find the almost. Now, there's the usual way to get a pendulum's equation. You draw all the forces, split gravity into components, chase the geometry. It works. But there's a second road, cleaner, and honestly more powerful. Instead of forces, we follow the energy. A moving pendulum carries two kinds of energy. Kinetic energy, the energy of motion, is 1/2 times the mass times the speed squared. And potential energy, the energy of height, is the mass times gravity times how high it sits. That's the whole cast, motion and height. Here's the key. In a vacuum, energy is never created or destroyed. It just trades hands. So the sum, kinetic plus potential, stays exactly constant. At the top of the swing, the bob stops dead. All height, no motion. At the bottom, it's flying. All motion, no height. Back and forth, the pendulum just pours energy from one pocket into the other. So let's release it from rest, at some starting angle we'll call theta 0. As it falls, the height it loses turns into speed. Set the kinetic energy it gains equal to the potential energy it loses. The mass cancels on both sides and out drops a beautifully simple result. The speed is the square root of 2 times gravity times the drop in height. But speed along the arc is really just the length of the pendulum times how fast the angle is changing. So this speed equation is secretly an equation for the angle. Rearrange and we get the rate of change of the angle equals the square root of 2gh over the length. Now we just need the height drop in terms of the angle. A little right triangle geometry does it. How far the bob hangs below the pivot is the length times the cosine of the angle. So the drop from the start down to here is the length times cosine theta minus cosine theta 0. Plug that in. And here's what makes the energy road special. Put it all together and you get a single first-order equation. The rate of change of the angle equals the square root of 2g over the length times cosine theta minus cosine theta 0. One derivative. Not two. The force method hands you a second-order equation. Energy hands you a first-order one for free. And if you don't believe it's the same pendulum, just differentiate it once more. The square roots cancel, the 2's cancel, and you land right back on the classic equation. The angular acceleration equals minus g over the length, times the sine of the angle. Same physics. We just arrived by an easier door. Now for the real payoff. Flip the equation over. Instead of how the angle changes with time, ask how time changes with the angle, and integrate over 1/4 of a swing. That gives the period at any amplitude. 4 times the square root of length over 2g, times the integral from 0 to theta 0 of 1 over the square root of cosine theta minus cosine theta 0. And here's the twist. That integral has no answer in terms of the usual functions, no sine, no log, nothing elementary. It's what's called an elliptic integral. You compute it numerically, or read it from a table. The pendulum, this simplest of toys, hides a genuinely hard integral inside it. So what does that integral actually say? For tiny swings, it collapses to Huygens' famous result, 2 pi times the square root of length over gravity with no angle in sight. That's the period doesn't care about amplitude rule. But as the swing gets wider, the period creeps up. A pendulum yanked out to a big angle swings noticeably slower than a gentle one. So Galileo was right, but only in the small print. Isochronism, equal times for every swing, is a beautiful approximation that holds only for gentle swings. Push the pendulum hard and it slows down. And the lovely part is how we saw it. Not by wrestling with forces but by letting a single idea, energy is conserved, do the work. Sometimes the shortest road is the one that just follows the energy.